Hey, what's up guys? Happy Sunday to you. What I've got today is basically just a little odds and ends video. So the first thing we're going to do is I'm going to answer a question that somebody had asked me about DC versus AC coupling on an oscilloscope. Well, let's do it like this. Let's introduce a sine wave signal to the oscilloscope. All right. So this is 33.53 kilohertz, but you know, the frequency doesn't matter here. What matters here is this is the 0 volt line, and the sine wave is above the 0 volt line instead of centered on it, which means this signal has a DC component. And if we count, this is 20 volts per division. So 20, 40, 60. We are looking at a DC component of 60 volts for this signal. Now, if we AC couple the signal, the signal now comes back where it is centered about the 0 line. Now, of course, we have to readjust our triggering, but that's not a big deal. And while we are still at 20 volts per division, our signal is now 20 volts positive, 20 volts negative. So we eliminated a 20 volt DC bias to this circuit. We bring up our measurements here. Our peak to peak is 49.6 volts now. So I hope that answers the question on AC versus DC coupling, because basically all it does, when we are on DC coupling, it lets both AC and DC pass through, signal parts pass through. But when we put it onto AC coupling, the DC component of the signal is completely blocked, and only the AC component is allowed through. All right, you guys remember the fidget spinner tachometer project we did a few days ago. I was talking to one of the subscribers, our friend Fred from Germany, who happens to be a a software engineer. Sorry, Fred. And we got to talking about how the code could be better modified. So over here, we have my original code. And then over here, we have the code that Fred has gone through and modified. And if we come down through here and we look, you can see he has done a display interval, increase the max interval time, and we now have a smooth RPM using a little function that Fred has created. So if we come down here, we see we have our prototypes now are functions of a float type and our standard void type. And then we come down here to this function, the float get RPM. So let me go down here to my old get RPM. We're kind of starting with the same thing where we're grabbing the current time, but now we've changed it to have these two variables, pulse 1 and pulse 2, and a Boolean flag waiting for low. So the while is still the same basically. And we say if a digital read Hall sensor pin is high, which means there is no signal detected, then basically nothing happens. And if not waiting for low, then waiting for low equals true. And if pulse 1 does not equal 0, pulse 2 now equals our micros. And if, where are we at back up here, the Hall sensor pin is high, then pulse 1 equals our micros. And then we have our logic here. If pulse 1 is 0 and pulse 2 is 0, we return as 0. And then we have our RPM, or RPFs in this case, equals pulse 2 minus pulse 1, the difference between our pulses, multiplied by 60 to get us our RPMs. Oh, so I got RPS is rotations per second. We change it to rotations per minute. It's returned, and then we can print it out. We also have this digit count function going on here, and a template of type T. Wow. Okay, I have to admit, you have gone beyond my programming ability here, Fred, so I am not even going to try and explain this anymore. But it works great. I am going to put a link to this code in the description below, along with a link to Fred's YouTube channel, Electronic Savage. So check it out. He's got some neat stuff he's doing, making an ultrasonic knife. All right, guys, so here we are out in my backyard. It's dusk, and some guys asked about how bright the LED light was. So I've mounted it on the house. And you can get a pretty good idea. That's just mounted with that 3M tape. Nothing permanent. But it's switched on at a good, oh, this is where I was when it switched on, so we're talking good 20 feet away. So yeah, that's pretty cool.